Welcome everybody to this morning's session, and let's get started with Dr. Amit Acharya, who will do about continuum mechanics and dislocations induced by meso macroscale engineering plasticity.
Good morning. So I'd like to thank the organizers for the invitation. I wasn't here six or whatever years ago. I was here in 2014. For those of you who don't know me, I'm an engineer. I have some interest in mathematics, so hopefully that helps in solving problems that I'm interested in. So this is joint work with, these are three gentlemen, ex-students, gotten PhDs in my group. And the theme of this talk is basically macroscopic plasticity. That's my main interest, and results from dislocation motion in an elastic medium. So somehow put these two concepts together. So that's the idea that we want to develop here. Okay, so what's a dislocation here? I need to tell you right from the beginning. So what it is so forget about this little thing over here, but think of this is a cartoon for a lattice, and all of us are familiar with the fact that you take a lattice, you put say some little shear, you take the load off, it goes back to its original shape. If you do it hard enough, at some point it doesn't go back to it. You take the loads off, it doesn't go back to its original shape, and that has to do with the fact that essentially there is periodicity in the lattice. But so what you might think of that situation as this is a slip plane, and this business of not going back has to do with these atoms here changing their neighbors. So something that was here now has moved over here, its nearest neighbor will be here, and so on and so forth. This is a slip plane. This stuff is color coded. So over here you might say this part of the slip plane, there's slip taken place, not over on this side, even though there's elastic deformation. And so a dislocation, one definition is it's the boundary between slipped and unslipped regions on a slip plane. Okay, so this part will be slipped, this part is unslipped, this is the boundary going through the plane of the paper. Okay, so that dislocation line. And if you take those words and you just play with it a little bit, you will see just from the logic of saying this that such a line cannot end in the material. It either has to go from boundary to boundary, or it has to be a closed loop. And this mathematically shows up as divergence-free fields. Okay, so that's one thing. And okay, so that's the dislocation line. Now it's characterized by it has a topological attribute, and so let me tell you about that. So this picture is exactly, well, okay. So I should also explain to you what dislocations are some things that were discovered before theoretically. I mean, they were postulated theoretically and discovered later experimentally. And the idea was related to what something Carnegie was saying yesterday. Usually, you see these kinds of slip steps even under an optical microscope, sort of a larger scale. And the question is, what causes slip? So suppose you said that, one thing would be that suppose it slipped here and it went right through, so it slipped one, right? So you take the slip plane, and Frankel did this calculation back of the envelope. You do this calculation and you'll find that actually, if you had to break all the bonds on the slip plane, the situation would be, it would take you, gigapascals of stress. And plasticity happens at megapascal stress levels. So clearly that cannot be the explanation. So what was the explanation? So Taylor, Orowan, Polanyi, Cambridge is a good place to talk about this. 1933, they said it must be because there are defects in the material, and then they rationalized dislocations. All of them had a different way of thinking about it. And the idea is that actually not all the bonds are broken at the same time. So it's this analogy with pulling the carpet on a frictional surface, right? So one way to do it is to pick up the whole surface and put it by a certain amount. That requires a certain amount of force. Instead, you can put a rock in the carpet and move the rock out. That just requires breaking a few bonds at a time. So you see, this is the guy. Then this guy will connect to this guy will pop out, so that's that configuration. And you break a few bonds at a time and you move the dislocation along. So that requires much less force, but you're putting, it's going to take time and it's going to be a dissipative process, and that's how it goes. And that's why you have megapascal stress at which you can have slip. Now, okay, so that's that picture. The other thing to keep in mind is how do you characterize a dislocation? So in the deformed lattice, let's say this is where some problem occurs, right? Okay, so you go to good parts of the lattice and you do a bunch of 3 steps over to the to sort of my left, and then you go 2 steps down, more or less following neighbors, and 2 steps down, 2 more this way, 2 more up, and you close this circuit, right? And now you do the same thing on a deformed lattice, undeformed lattice. So you go 3 this way, 2 down, 2 this way, 2 up. Of course, there's going to be a deficit because you have 1 atomic plane matching, missing there. And this you can right away see that no matter how big a loop you do this on, because that atomic plane is missing, you're always going to get this deficit. And this is called the Burger's vector of this dislocation. And in this dislocation, it's particularly called an edge dislocation. An edge is where the line through the plane of the paper is perpendicular to the Burger's vector. Okay, defined this way. In the undeformed lattice, see, the vector direction also is completely no problem. There is no deformation there. So you can pick this up. And for okay, so that's the beast. And okay, so the other thing to keep in mind related to dislocation, you see that this is called the core. Around here, the bonds are going to be messed up. So there's going to be stress. Even if you don't put any loads, this is a characteristic of dislocations in the body, that, okay, there's going to be stress in the body, and these are actually fairly in 2D long range. It's 1 over R decay, even linear elastic medium. So this is a pretty high level of stress okay, so we can think that we try to minimize energy when we can. So that's a high level of stress. The body never wants to have that much energy and stress in it. So typically what you'll find is dislocations will always occur as dipolar pairs or loops, because that minimizes, that's a much less energy than. So you will never find one dislocation popping out in the crystal, okay? Even in a 2D setting, it'll mostly be dipoles. You do any simulation, you'll find that, or there'll be loops. That's basically the idea you want to carry. And typically what we're going to characterize it is by a tensor, which is the Burger's vector tensor product with the line direction locally. So you follow this. So that's all good. I motivated this in terms of the edge dislocation, but these things are, I said that, these things can, these are curves. They can be curves in the body, and Burger's came up, same Burger's of Burger's equation, fluid mechanics. His brother was a crystallographer, so he learned some crystallography from Burger, and he came up with the screw dislocation. The screw dislocation is interesting. So this, if you think about this situation, so you make a cut in the plane and then you shove in this part by 1 atomic distance. So that would be the Burger's vector. And for a screw dislocation, the Burger's vector is parallel to the line direction. And edge is when it's perpendicular. Of course, the line direction is changing, Burger's vector remains fixed, so you can have mixed character of the dislocation too, as in this situation. See, here it's an edge, the line inside goes around, comes out here, it's a screw here. And so this can be loops, and clearly you right away see that this business of characterizing this stuff by a Burger, at least for me, this is a fantastic reduction in complexity. If you have to think about every little dislocation line and how it's doing what it's doing in a lattice with a whole bunch of atoms, it's almost impossible. So this is a fantastic, in my opinion, compaction of ideas. All right, so that's that. And what does it allow you to do? These dislocations, what you can do is you put stress. Okay, so they have stresses, and they interact through their stress fields. So this guy produces some stress, 1 over r, let's say in 2D. There's a dislocation sitting here. It sees the stress of this fellow, vice versa, and applied loads. And this is how you move dislocations in the body and cause very large plastic deformations without the body falling apart. And this is an example of what it allows you to do. From solids, there are only two things that can happen. Either it doesn't fall apart when you put lots of load and it does plastic deformation, large deformation, or it breaks, fractures. So that's that. And I told you about dislocation. So if you look at it from plan view, these are pictures of loops. Here it's edge on. This is in fatigue loading. These things form interesting patterns. So here the line is going through the plane of the paper. And as fatigue means you reverse the load, and you keep doing that, they arrange themselves in these sorts of patterns where they will localize around walls. These are cell walls, okay? And then you can have patterns like this too. Why do we care about this kind of stuff? So the topic is new materials. Plasticity is an old subject. It applies to new materials too. But so for example, all for whoever took a flight to get here, all your turbine engines, the jet engines, and even for power generations, you have blades are single crystals, turbine discs are polycrystals, okay? And this is extremely important to be able to, because to be able to say fatigue loading, because you start up this thing, put it down. These are fatigue cycles, and dislocations move, so you don't want a fatigue crack to run through a blade. This is the last thing you want to happen. And so to be able to understand these things is important. Plasticity is important for that. Of course, a holy grail is high strength, high ductility, lightweight alloys. You always want high strength and high ductility, meaning you want it to go up to it can handle large stresses, but once it gets there, it doesn't completely fall apart. It can do ductility too. It's very difficult to manage these two competing claims. And you want lightweight, like magnesium alloys, but then you don't want it to be brittle. So this is for material design, this is important. And apparently for low greenhouse gases, but where I come from now, apparently greenhouse gases don't matter. So, okay, so then other applications are stress and defect management in semiconductor thin film. So you have you want to put down a semiconductor film on a substrate. You don't get semiconductors in bulk form, so you do epitaxy. This thing grows in a state of self-strain, and you want to grow the film as thick as possible, but you don't want any defects on the interfaces or threading dislocations. So that's another area where this thing comes up. Similarly, in interconnects, connecting chips, the thermal mismatch. So you have substrates, you have metals, there's very high temperatures because of the resistance of these very thin wires. The metal is wanting to do something different from the substrate. You have huge thermal mismatch stresses. You don't want the interconnects to break. Again, it's a question of plasticity. So one of the things that happens in terms of modeling, difference between the macroscopic plasticity and microscopic is the following: zeroth orders. Forget about patterns and all that. At macro scales, you do a stress-strain behavior for a material. You take one, you pull it, and the basic output from an experiment is force displacement. But for the same material, if you did force displacement, people who do solid mechanics, you learn this when you're a sophomore or freshman, that force displacement is not a material characteristic, okay? So for the same material, force displacement curves will vary depending on the geometry of the specimen. But stress-strain curves, macroscopically, are not dependent on the geometry. This is why you reduce it to stress, force per unit area times length over deformed length, the displacement over the original length. This is not dependent on size and geometry. So there's a material characteristic. Turns out that when the characteristic length scale of the specimens go down below 50 microns, then even stress strain depends upon size. And this is the sort of, if you didn't get anything right when you go to smaller scales, this is what you have to get right. Not an easy thing. So, but that's okay. So that's the thing. The elasticity, macroscopic plasticity, all of this is size independent. Okay, for homogeneous materials. Very good. So, so now I'll start talking about model and some predictions from that. Okay, so the equations are for those of, I mean, yeah, this is balance of mass, balance of linear momentum stays the same. For those of you who do elasticity, you know, so W, think of this as the inverse elastic distortion. And I say distortion because in this case, this thing is not curl free. Okay, so this is the main thing. So that's what characterizes dislocation. So that the Burger's vector I showed you, because if this curl is non-zero, then when you map to the reference, you see you're going to get a deficit. So so this is the first difference, and then because of the fact that it's a curl, divergence of alpha has to be 0. This has to do with the fact that these are loops or lines go from boundary to boundary. Now, for this thing, this is, for those who like the fancy, you know, this is a vector value 2 form. So it's something that lives on areas. It's a density on areas. So then if you do a balance law or a conservation law, so this is the Burger's vector content in any deforming area patch. So alpha acting on nu is the normal to the patch. So that gives you the Burger's vector content. You look at a time derivative of that guy. And then you do some it's interesting calculus, but if you can do that, you'll see that the flux will be characterized by alpha cross V. This is a vector value 2 form. So V is something that's moving these lines. And so this statement is about take an area patch that's moving with the deformation. You look at all dislocation lines threading this patch. They have Burger's vector. You're taking the sum of the Burger's vector. How does the Burger's vector content of this area patch change with time? And the flux corresponds to this object over here. This alpha cross V, just like for volume density, rho times V is the flux, right? So here it's this, and this thing, because it's a 2 form, then when you peel this out, you know, it'll be this derivative. So yesterday there was some talk with the magnetoelastic situation whether something should be. So you see, this doesn't convect like a 3 form, like a linear momentum is a vector value 3 form. So that does a different thing, like the convection. But here it'll look like this. So that's the evolution law. And then if you write it in Eulerian form, for those of you who do fluids, you know, this starts to look very much like a vorticity equation, except dislocations move with respect to the material. So consequently, there is this capital V, which is the velocity of the lines with respect to the material. Okay? And now if you take this equation and you mix it up with this and that, you will see that an evolution for W comes out to be this particular thing. And now if you define this W to be, its inverse to be the elastic distortion, these are all defined locally now. Okay? I mean, at every given point you have an FE. So what comes out is an additive decomposition of the velocity gradient. This is the velocity gradient. So the elastic part and a plastic part. Okay? So there's no, for those of you who know a little bit about plasticity, in this theory, there is no multiplicative decomposition. There's no reference. Okay? There's no coherent global reference configuration for this model. It's much like a fluid. Because for plasticity, it doesn't make sense to know some coherent reference from where your chunk of material in the hardware shop came from. So that's that, and that's the theory, and I make some comments over here. So the only state variables are from here and now: current configuration, dislocation density, dislocation velocity, material velocity, mass density, and the elastic distortion. These are all measurable in the current configuration. Okay, very good. So if you wanted to solve the best way, I mean, if we were clever enough, then the equations and here at this level, you're thinking of resolving dislocations every dislocation is being resolved, okay? So the equations you'd want to solve is this one, this is a system, and say, okay, forget inertia for now, but we do inertia calculations with inertia too, but it'll be this. It's nicely, compactly written, but this is really, really hard. I mean, everything is hard here, but at least for us. But this is really hard. Why? Because you see, this V will have a constitutive equation dependent on stress. And you can do thermodynamics on this, and all of this works out nicely. You get something called like the Peachkeller force on dislocations with a little bit of a twist. But V will have a constitutive equation based on that. So it will be stress and depending on curl W. So you put that in there. You see there's a curl W here. There'll be a curl W there. It has to be, I mean, even if you do the simplest thing, this has to be, V has to be linear in curl W. So you have a quadratic in curl W here, and there's no conservation form on that equation. So this is really, really hard, okay? And then T is T. So because we have to, I mean, I work at a place where there are very, very good mathematicians, okay? And they like to talk to practical people, I mean, so people like me. All right, so, and I've talked to pretty much all of them who I needed to, and they say this is pretty hard. You really cannot say much mathematically about such things. So as an engineer, you know, you can't sit and twiddle your thumbs and say, I can't. I mean, that's not an option. So you do what you can. So we have to compute. But even the computing, you have, obviously anyone who's done any computing knows that, you know, if you just go sit blindly, do something, it never works. You have to do something sensible about this. So what we did was, you know, you take the W, you do a Helmholtz decomposition of this, and so that would be, its gradient would be, this guy's gradient, this is a vector field. Gradient would be the compatible part of this, meaning the gradient part, and chi would be the incompatible part. And then you can, this equation, instead of solving that, you solve this equation, which still has a conservation form. So you can at least move one set of derivatives onto test functions, etc. Anyway, so that's that. And the way you solve the stress problem is, suppose you're given this, then you solve for the incompatible part. You stick that into the W, go into there and solve for the F. Okay, so now let me show you some, okay, that's that, show you some results. At the microscopic level, okay? Meaning you're resolving every dislocation. So one question is, you know, I've heard this all my life. Apparently, you know, if you're doing dislocations, you do linear elasticity, and if you can't do, if you do linear, and beyond that, apparently, unless you do quantum mechanics, nothing matters. Everything linear elastic fields are very, very good. You know, just away from the core. If you've grown up with general continuum mechanics, this doesn't quite sound right, because, you know, there are pretty high stresses and strains. So what? Nonlinear elasticity doesn't matter? Well, okay, so fine. Now we have a tool by which we can compute such things. Okay, so you put a little core in there, and it's a 100 Burgers vector size domain. And this is a comparison of the difference between the linear elastic and the nonlinear elastic fields in the stress. And it turns out that for the core, up to, so it's a Savannah-Kirchhoff material. We are solving the Euler-Lagrange equations. Okay? So okay, not Euler-Lagrange, but the equations I showed you for the stress field. So there are 10% differences in the full stress up to 10 Burgers vector from the core. Okay, and this actually matches with some results based on orbital density functional theory by Gavini and Toffoli. There are differences between linear and nonlinear theory. Okay, the other one is you take the edge dislocation. This is in the shear stress. So everyone will show you, I mean, not everyone, lots of people will show you, you do the nonlinear elastic field, linear elastic field. They show you the shear stress field on the x-axis. No difference, zero difference over here. This is also a plot of the differences. However, along these diagonals, up to 120 Burgers vector from the core, there are 10% differences in the stress field. So if a dislocation over here, p scalar force moves, this guy moves because of the stress from this, up to 120 Burger's vector, there are 10% differences in the stresses they'll see. Very good. Now we can put these things to the test. Okay, there are differences between linear and nonlinear theory. So when does the linear theory and nonlinear theory start to match? If you knock down the Burger's vector strength by 50 times, that's when things start to become quite good. Okay, and then there are some, okay, so here we show you that this is, you impose the velocity. That's not how it works. Actually, dislocations work with the stresses, but two opposite signs, and you impose the velocity, make them move, and we can do the annihilation. Okay? This is not easy, even with impose. So if you think about computing this and getting it to concentrations to move like that and going to zero, that's that. Along the path of a dislocation, you produce a slip step at the end when the dislocation exits. This is a stress-free body. So you produce stress-free strain because dislocations move. And this is a situation where you push the dislocation, so this is with inertia, you push the dislocation faster than the shear wave, linear elastic shear wave speed of the material. You're supposed to see Mach cones, and you do. And we have many more results for the coupled setting in the papers that we've done. Okay, so that's from the theory. So how am I doing on time? When do I end?
We have about 15 minutes.
15 minutes.
Plus a question.
Very good. Okay, so I'll just take my time, tell you as much as I can. We have many results, but let me just show you some things here. So polygonization. Okay, so this is something. So what's the idea? The idea is you take a beam and you suppose you want to bend it by a certain amount. You can either do it elastically, it costs you a lot. So what does the material do? What the material does is it basically puts out these dislocation walls. So if you wanted to do it elastically, then of course there has to be stress. One way of doing it with zero stress is to put piecewise rotations in there, separated by dislocation walls. These would be high, depending upon how much you're putting, a high angle boundary or a low angle grain boundary. And this would make it zero stress. And this is observed, so this is new materials here. This is still a challenging problem. This is before even I was born. So this is 1955. It's a single crystal of zinc. It was bent around a mantle, and these are the dislocation walls, and there's the rotations of the slip lattice, and this is when it breaks along a slip plane. Okay, so what the idea is, you want to put dislocation walls, and that then makes it zero stress. Okay, very good. So what's our calculation? I'll show you a very simple calculation of this. All we are doing is we'll start with creating this wall by sticking in dislocations. All right? So here there's 1, there's 3, 1, 1 over there, 1 over 5, 10, 20, 30, 36, 45, 50. We just want to see how you can calculate the whole stress field is calculated, but we'll look at the strain energy. Kirchhoff. Here, this is for 1, 3, 5, 10, 20, 30, and then there's like a phase transition that happens. Because you know that when there is one dislocation, there's a lot of energy in the body. This we know, the one stress field of one dislocation. When there is a wall, there should be no stress, elastic stress. This also we know. Something interesting has to happen in between. We can actually compute that. So that's what we're doing. You see the fields go like that, and then there's like even computationally, there's something interesting that happens in between these two. So the energy completely concentrates on the wall. 45, 50, there's almost nothing. We brought them very close together. Okay? So, so we get the physical result. And then there was this mathematical result, which is of course correct, done by extremely good people, but the results don't square. And so I wanted to take a little bit of time to explain to you what's going on there. So, this is 14, and when I was making the slide, I wrote reset. Then I'm thinking 14, reset. I guess when you get older, your time scale shrinks in your head or something. I don't know, something like that. Okay, so I'll just give you the general idea of what's going on over here. Okay, so think of this configuration. There's an R1, there's a high angle boundary, R2, grain boundary here, and and H is the dimension. So Muller-Scardiese-Pieri have this result, it uses the generalized, this is extremely hard for me, okay, so it is not any, I don't know, it's tough to read for someone like me, but I could sort through the theorem. And the statement, basically they use a generalized rigidity estimate and a well-separatedness assumption of the course. So the idea is this, you take a deformation gradient sequence, F epsilon, let's say curl goes to this measure, for every epsilon there is a measure which tends to mu, and these convergences are of course in the right sense, of course, when it's weak, it's weak. So the rigidity estimate gives you that for every F epsilon field, there is a constant rotation field, R epsilon R. This does not vary in the body, okay? So that's my thing for the R. That's R1, this is R2, this is the R. There's a constant one that tends to R, and then you take the F epsilon, which varies with position, you hit it with the R epsilon transpose, so you kind of get rid of some of the rotation, and that you call beta epsilon, minus an identity, but don't worry about that. That tends to beta. And then the gamma convergence result is that if you took a nonlinear elastic energy with the right growth conditions, etc., so sequence of the energy is integrated in the body, this gamma converges to, this is the elastic term plus something on the grain boundary. Okay, so forget about this. This is not important. This part is not important for this talk. It's this part that we'll focus on. So you see, what's going to happen is, this is a high angle boundary. So there's an F epsilon. This guy is a constant. So think of a situation, just every element of the sequence is just a constant guy. Constant meaning it's the same F. So if it's a high angle boundary, you hit it with a constant rotation transpose, you're not going to be able to kill the rotations of the varying rotations of the F epsilon field. Okay? And now, this part of it, this is the linear elastic moduli, which has minor symmetries. So it works on symmetric tensor fields. Okay? Now the point is, we know that this sequence, by any means, if you take that sequence, that is going to 0, no question, as epsilon goes to infinity. This fellow absolutely cannot go to 0, because it has minor symmetries, and beta is not a symmetric tensor, neither is it a skew-symmetric tensor. Because you cannot kill the rotations of the two sides of F epsilon, bipolar decomposition, by a constant rotation. So you can kill one side or the other, something average, but it's not going to go to 0. Okay, so what gives? This is obviously a correct result. So then you sit and try to think about the hypotheses. And discussions with Janusz Ginster helped me sort this out. Okay, so that's that. So the rigidity estimate, in this case, you have piecewise constant rotations, and you have this R, the constant guy, and the rigidity estimate then gives you, usually it's for the compatible case, but here you have dislocation, so it's this. So you have this, the field minus the constant rotations is L2 norm is bounded by C depending only on the omega, and then the distance, L2 norm of the distance function of pointwise F epsilons to rotations, and then the total variation of this measure, the curl Fe. So in this particular case, you can just explicitly calculate a piecewise constant rotation. I can even do this calculation. So you do this is not 0. This guy is 0 because it's rotations everywhere. And this guy, you can calculate out the total variation of this field easily. It's basically R1 minus R2 acting on the tangential guy, take its norm everywhere, integrate on the grain boundary. So this thing, yeah, this is true. This gives you no control on making RE close to F epsilon. So what actually did this result for them is the well-separatedness assumption. So you say that the cores have to be well-separated, and it's a pretty intense assumption. It takes quite a bit to sort this out, for me at least. And the point is here, it's not well-separated. And you saw that in the picture over here. So you see, when it's not well-separated, then you have energy. But then when it gets very close, that's what allows you to completely shield the fields of the dislocations in the wall, goes to zero. So the conclusion really is that the F epsilon corresponding to a high angle grain boundary is not an admissible sequence for the Murarska-Diaz-Pieri result. Okay, but yeah, okay, so that's really the conclusion. Okay, so that's one. And then what we have is over here, so then you want to do something at a slightly, okay, good. Let me just explain one. So now you want to, okay, so until now I've been talking about things where every dislocation is resolved, so to say, right? But of course, you want to do macroscopic, mesoscopic plasticity. Not every dislocation is going to be resolved. So let's think of how you might say, there's a homogenization question here of that really complicated underlying equation set. There's no mathematics, apparently, that, as far as I've been told. In the microscopic theory, existence is not known, homogenization, forget it. So nevertheless, you've got to do something. So how do you try to think a little rationally about that? And the idea is, suppose you take some field that's varying rapidly. This is like some poor man's with convergence. You take a running, space-time running window, and you average those fields. Okay, so that's bar is average. Now take the original equations, assume everything in sight average is the same as the unaveraged guy, except the plastic strain. See, this thing has, this is a strain rate. This has units of 1 over L, this is V, length over time. So that's a plastic strain rate due to motion of dislocations. So when you average this fellow, this is one place where deep curl and all that doesn't work. And you can almost see that physically why it will not work. So you say this average minus the average of the product minus the product of the averages is, if you just wrote this out, this is just algebra and calculus, there will be a 4-index object sitting there averaged. This we are going to call the macroscopic plastic strain rate of the unresolved dislocations. And what goes on over here is the following. That suppose you have a loop, and this is the averaging volume, okay? So alpha cross V, alpha is of this form. You see, alpha bar is going to be 0 because this edge cancels this one, this guy will cancel that one. The V will also, this guy will cancel this guy will cancel that. V bar is also 0. But when you do alpha cross V, there's an L cross V. An L cross V on this segment adds up to the L cross V on that segment, and similarly for these. So when a loop expands, you forget about average dislocations, average velocity. But the plastic strain rate you're going to sense macroscopically. And you absolutely have to model this. And this is what we interpret as what engineers have done, or they've forgotten about all dislocations, forget it. Large scale is the plastic strain rate that matters. And you have to come up with a constitutive equation for this. So we'll assume constitutive, and so in the microscopic theory, you replace wherever there's an alpha cross V, you put in an alpha cross V plus LP. LP, you give a constitutive equation. It's phenomenological, but it's very measured, and everything can be measured there, and you go ahead. So let me show you some results. Okay, so because of the structure of that alpha equation, even in the average sense, there is a natural jump condition that comes up and a boundary condition, and that has a lot of significance. That is new to plasticity, and one of the significant parts is the jump conditions comes out to be So basically, when you forget about all kinds of other details, you'll have that the jump in the flux crossed with the normal has to be 0. So this says that across a grain boundary, the two crystals have to talk. And if there's a plastic strain rate there, classical crystal plasticity strain rate, this jump condition actually depends on all 5 grain boundary parameters, okay? The misorientation across a grain boundary and the 2 parameters characterizing the orientation of the grain boundary. It shows up in the theory. So this is classical plasticity for the LP part, which we are going to phenomenologically assume. And then we have this other addition from the microscopic theory. And let me just quickly tell you about one experimental result at the mesoscale, which is interesting. And everything that I'm going to talk about, our prediction, has nothing to do with the phenomenological assumption. It's about the structure of the theory. And so let me tell you what that is very quickly. These are micropillars, ceramic micropillars with a metallic thin film. And you're going to do nano indentation on this, and you can see the scales over here, okay? So you do nano indentation when the thin film is in the 90-degree orientation to the loading axis. What you're plotting here is the log of the film thickness. It's a polycrystalline film. And here, it's the log of the stress that you get, the nano indentation stress. The relationship experimental, when in the 90-degree orientation you get, is a -1 exponent, log of the stress versus the log of the thickness. It's a scale effect, log of the film thickness. Elasticity, conventional plasticity, you'll get nothing, because there's no intrinsic length scale. You turn this guy around, the thin film now is in a 45-degree orientation to begin with, and then you put it in. So if you have some solid intuition, you immediately see that the film will get put in shear. And then what happens is that it breaks. It fractures like this. Lots of deformation. Here, none. Same, ceramic material, the thin film, and you just change the orientation. This is the effect you get. But in the size effect, there's almost no size effect, okay? Now there are strain gradient plasticity theories, etc., etc. They'll say that the boundary conditions are all murky. If you don't, okay, so there the question is, if it's a ceramic and a metallic interface, then apparently there is some dislocations cannot go through, okay, whatever. And then so there's going to be a blocked hardening. Okay, and so if you did something like that, what you get is that for both cases it's still a ceramic and a metallic interface. The answer is -1 exponent. But actually, when you just turn this orientation around, the exponent is nothing, 0. So what happens? Okay, so this is the constitutive structure. Forget it. Anything I'll tell you about it, I'll just explain it, that it's not because of the constitutive business. So we set this up, we can do this calculation, but I can explain to you what happens here in our model and why it predicts the thing is very clearly, even without putting it in a pillar. So take a simple shear of a block. Okay? And in our problem, you can put blocked boundary conditions. So this is the boundary condition. And you can set this to 0 to get a blocked boundary condition. So you're doing the simple shear case. If you think about what this really means, is what it does is at any boundary, it will allow you shears like this. Because an edge dislocation, you can block this as much as you want, an edge dislocation can go like this and shear the bottom. But if you wanted to go like that, you simply cannot do that. That is blocked. That's just a characteristic of this boundary condition. Now, when you do the simple shear, you're putting it in shear, there's no size effect. The little bit of it is that because of those of you who know J2 plasticity, if you have a shear like this, you'll get a plastic strain rate like this too. That's the guy that gets blocked, so you get a very little shear. And so there's no size effect, and these are with different levels of strain, okay? You turn so now you do, the next one is, you take this block, now in the 90-degree orientation, now you're compressing it. If you didn't put any lateral constraints, then again you don't get any size effect. But when you put the lateral constraint, there are big gradients that get set up, and you get a size effect, okay? That's basically what it is. It's the boundary condition of the theory. It has nothing to do with constitutive assumptions, blah, blah. And so, we did it for the actual. This is in ACTA, the paper. We get that, and this is an experimental plot of the film. The film actually expands out. There's fracture along the interface. We get that. We didn't allow for fracture, so that's that. And in this 90-degree, 45-degree orientation, there's not a size effect, etc., etc. And I think that's a good place to stop. Thank you very much.
A little time for a brief question or comment.
You mentioned this gamma convergence result in the
Yes.
middle,
Yes?
where you had the issue that, or where the result has the issue that basically do you just get a single rotation by geometric rigidity?
Yeah, geometric rigidity says that there is one singular, but it doesn't give you much control in this particular case.
Yes. I think more recently, and I think on the scale of the last, I don't know, 7 years, there might, I think there was there are now versions that can handle more.
Okay, maybe there is, but I don't know of any result that this is the second iteration of the scaling. The first one was Carnegie where it became uncoupled because of the scale. So that was I believe that was an epsilon squared scaling. This one is with epsilon squared log epsilon squared. So it's a little bit higher, but it's the well separatedness that gets, all of this requires well separatedness. That's built into the game. So I wouldn't say there is a problem. It's a result by itself.
Yeah, but yeah.
This thing doesn't fit into that scheme. I mean, you cannot talk about the high angle boundary as an admissible sequence for their result. That's all I'm saying. I mean, but it's.
I was asking if more recent results would be able to have that.
Not that I'm aware of. And I think there are.
Questions? Okay, if not, let's thank the speaker.